Module 5.2, Inverse Functions and Exponential Functions. This is chapters 4.1 and 4.2 in your book. 5.2 opener. The study of inverse functions leads to an important relationship between exponential functions and logarithmic functions. As we will see later, exponential functions and the properties of exponents are used to study trig functions. So that's why we're going to look at them now. Some important concepts to focus on. You should be able to easily find the inverse function of a linear function. So if you have a function that's linear, you should know how to find its inverse function. You should be able to use the properties of exponential expressions, which we've already gone over, to work with exponential functions. Right? Same idea, just different name. And you should be able to work basic interest formula problems. One-to-one functions and inverse functions. A function f is one-to-one if f of a is not equal to f of b when a is not equal to b. In other words, when the inputs are different, the outputs should be different. When whatever goes in, if a is not equal to b, then f of a should not equal f of b. So, for example, why is f of x equal to 2x plus 3 1-to-1? Well, if we were to try different numbers, all kinds of different numbers, if we plug in 1, f of 1 is 2 times 1 plus 3, and then look at some other number, f of 2, that's 2 times 2 plus 3. But 2 times 1 plus 3 is 2 plus 3 is 5. 2 times 2 plus 3 is 4 plus 3 is 7. So when 1 is not equal to 2, we get that 5 is not equal to 7, so we know it's 1-to-1. Right? We would have to check all the numbers. So instead of checking all the numbers, we actually need a test. And that's what we use the horizontal line test for. We look at the graph of a function, and if any horizontal line passes through the graph of a function more than once, then the function is not one-to-one. It's a little bit like the vertical line test, only it's a horizontal line test. And remember, the vertical line test is to tell you whether you have a function or not. The horizontal line test is to tell you whether you have a one-to-one function or not. So let's look at the graph of 2x plus 3. The graph of 2x plus 3 crosses the y-axis at 3, right, because of this 3. It's the y-intercept. And it has a slope of 2. So from there, it goes up 2 over 1, up 2 over 1. Okay. That's the graph of y is equal to 2x plus 3. Notice that any horizontal line we draw is not going to ever cross more than once. So that's how we know that the function is one-to-one. If f is one-to-one, then there is an inverse, and we're going to say that for right now we're going to call its inverse g. And its inverse is going to be defined by composition. So g is its inverse if regardless of which order you compose the functions, you get the identity function. In other words, if you do f of g of x, you get x, or g of f of x, you get x. And let me remind you what composition means. Here's an easy example here. If f of x is 2x plus 1, and g of x, 2x plus 1, and g of x is equal to 5x, f of g of x, that's a composition, means you're going to take g and put it into f, anywhere that x was. So this should say 2 times g of x plus 1. This should be g of x in here. But g of x is equal to 5x. So we could just put 2 times 5x plus 1. And the other order would be different. Okay. And we're going to call the inverse of f inverse. That's just a new name we're going to use for the inverse. F inverse. it looks like f to the negative 1, but we don't say it that way. Okay, so let's look at the composition of f and g for these two functions here. Remember, our symbol for composition was a circle. So f circle g of x by definition means f, and you're going to take g of x and plug it in there. So it's 5 over 2, because that's what f is, but instead of x, we're going to put g of x in there. 5 over x minus 2, right? And now this tells you you're plugging in g of x. So g of x is 2 over 5x plus 2. Right? So the 5 and the 2 cancel, and we're left with x plus 2 minus 2. So this is 2 minus 2, which is x. So we get the identity function. So far it looks like we have an inverse function, but we have to try the inverse the other way around. G of f, this is a circle, it's not a closed dot. Closed dot would be multiplication of x. So again, this is g, and you're plugging in f of x into g. So g is 2/5 of x plus 2. 2/5 of x plus 2. And we're going to plug in f of x. F of x is 5 over 2x minus 2. Then we're going to simplify. The negative 2 plus 2 cancel. The 5 over 2 and the 2 over 5 cancel, and then we're left with just x. So we get the identity function either way. That means that f and g are inverses of each other. Let's try the same thing for f of x equal to 3x minus 2 and g of x is equal to 2x plus 3. F of g of x is 3 times x minus 2, 3 times, again this is 2x plus 3, and we're going to multiply that out. This is 6x plus 9 minus 2. This is 6x plus 7. Notice we already don't have the identity function, so these can't be inverses of each other. We would only need an x, but we have 6x plus 7. Notice, and you might think that they're inverses of each other, because here we're doing 3 times x minus 2, and here we're doing 2 times x plus 3. But these are not exactly the opposite, okay? So you have to check these to make sure. These are completely opposite. 5 over 2x minus 2 and 2 over 5th of x plus 2 are opposites. Okay, so what if you're given a single function and you have to find its inverse? Well, the steps are always the same. You're going to switch the x and the y, then you're going to solve for the new y, and then you're just going to call it f inverse. Okay, so let's try. To find the inverse, and we'll come back to this note here in a second. To find the inverse of f of x equal to 3x minus 2, or y is equal to 3x minus 2, we're going to flip the x and the y. X is equal to 3y minus 2. And we're going to solve for this y, solve for that y. So we need to add plus 2 to both sides to get x plus 2 is equal to 3y, and divide both sides by 3, which would give us y is equal to x plus 2 over 3. And then we're going to call that function x plus 2 over 3 f inverse of x. So that's the inverse right there. And let's go back and graph 3x minus 2. 3x minus 2 crosses at negative 2, has a slope of 3. What about this function right here? This function is the same thing as saying x divided by 3 plus 2/3. So this one crosses at 2/3, not quite to 1, but almost to 1. And has a slope of 1 over 3. So something like this maybe. This note says the graph of the inverse function is reflected across the line y is equal to x. And that's what this shows. So the line y is equal to x is this line that cuts diagonally across. Y is equal to x. Cuts straight down the middle. And if you have one function's graph, like we did here, for y is equal to 3x minus 2, or sorry, this one was y is equal to 3x minus 2. All you have to do is reflect it, look at the mirror image, and you'll get the graph of the inverse function. Exponential functions. The properties of exponential numbers and expressions are the same for exponential functions. So all these properties you learned before are still going to apply. So we have an exponential function is equal to a to the x. So given that f of x is equal to 2 to the x, find f of 10. In other words, f, and plug in 10. In other words, 2 to the 10th. That's 2 times 2 times 2 times 2 times 2 times 2 times 2, 10 times, which would give you 1,024. Here's some properties of the function f of x. The points 0, 1, and 1, comma, a, whatever this a is, are both on the graph. So 0 for x, 1 for y would be here. That point is always on there. And then 1 for x. And then a, whatever a is, let's say a was equal to 2, like it is here. 1, comma, a is on the graph. So 0, 1, and 1, comma, a. If a is bigger than 0, then the function is an increasing function. So the function starts off really, really close to 0, but it increases rapidly. There's a graph of a to the x. And the domain is all the real numbers from negative infinity to infinity. So it starts off as small as you want it to be, but it's never quite equal to 0. And then you can get as high as you want to in the x's, all the way up to infinity. And it just keeps growing faster and faster and faster. The range is from 0 to infinity, because it's never going to equal 0, but it'll start somewhere close to 0 and go all the way up to infinity. But there's nothing less than 0 if a is positive. So we're going to sketch a graph of 2x plus 1. Remember, if you're not sure how to graph these functions, you can always just try x and y values. We're going to try 0, we're going to try 1, we're going to try 2. When x is 0, we get 2 to the 0 plus 1, or 2 to the first power, which is 2. When x is 1, we get 2 to the 1 plus 1, which is 2 squared, which is 4. When x is 2, we get 2 to the 2 plus 1, which is 2 to the third, which is 8. And etc. 3 would give you 16, etc. So at 0, we get 2. At 1, we get 4. So that's 1, 2, 3, 4. At 2, we get 8. At 3, we get 16, way up there. So notice it looks just like we were talking about before. It increases rapidly. We're going to solve for 16 to the 3x plus 2 equal to 2 to the 5x minus 3. We're going to solve for x in that equation. The easiest thing to do here algebraically is notice that 16 is 2 to the 4th power. You want to use that because we have a base of 2 here. So we want to write this 16 with a base 2 also. We want to have the same base. It might help. So instead of 16, because 16 is equal to 2 to the 4th, I'm going to write 2 to the 4th. And then it's all of that to the 3x plus 2. That's also equal to 2 to the 5x minus 3. And remember, our properties of exponents says that if we're raising one exponential expression to another power, we can multiply the exponents. So we're going to multiply them. This is 2 to the 12x plus 8 is equal to 2 to the 5x minus 3. Now, because the bases are the same, this 2 and the 2 are the same, and we're looking at an equation, we know that the exponents have to be the same. Right? The bases are the same, so the exponents should be the same. Otherwise, it wouldn't make sense. So we know that 12x plus 8 has to equal 5x minus 3. And now we can solve for x. We're going to subtract 5x from both sides. So 12x minus 5x is 7x plus 8 is equal to negative 3. We're going to subtract 8 from both sides. We get 7x is equal to negative 11. And then we're going to divide both sides by 7. And there we have it. Objective 3, interest formula problems. Compound interest formula. The amount A in an account after depositing an original amount P, earning an interest rate of R for T years paid N times per year, or compounded N times per year, is given by A is equal to P times 1 plus R over N to the N times T. So the amount after some time when you have the original amount P is given by this formula. So suppose you deposited $200, so your P is 200. Let's write it here. P is 200. That pays you 2% interest. In other words, your R, your interest, is not 2 but 0.02. Remember, there's a decimal here, and to convert it to a decimal, you always move it twice over. 1, 2, 1, 2. This is 0.02. Compounded quarterly, that tells you that your N is equal to 4. T is 10 years. So the amount after 10 years for $200 is 200 times 1 plus 0.02 over 4 times 4 times to the 4 times 10. Okay. And let's plug it into the calculator and make sure we're doing this correctly. Okay, so we have 200, we put parentheses, and always make sure to use extra parentheses just to be safe if you need them. Plus, or 1 plus, I'm going to put parentheses around this thing just to be safe. Just to group it together. 0.02 over 4. Oops, let me go back. 0.02 over 4. Close that parentheses. So I did this. Close that parentheses and then close another parentheses. And then I'm going to raise all of that. And I'm going to put that in parentheses too. 4 times 10. And close it. Enter. So rounding to the hundredths place, about $244.16. It's about $244.16 approximately. So you earned a good $44.16 on interest alone if you started off with $200, right? Not very much. The number E is an irrational number, and it's defined to be equal to approximately 2.718281, and it keeps going forever and ever, just like pi. But for the most part, we use 2.72. We round it to 2.72, just like for pi. Right? Pi is 3.1415, etc. But for the most part, we use 3.14. Okay. And E is actually found by compounding as much as you can, right? Letting this n get larger and larger and larger in that formula and fixing r. So just keeping r fixed. In this case, we let r is equal to 1, the rate be 1, and just seeing what happens. It turns out that the most optimal you can get is that 1 plus 1 over n to the n power. In other words, the compounding gets close to e, about 2.72. So for that reason, we look at something called continuous compounding, where the amount a, same as before, after you put an original amount p, is compounded continuously. In other words, it's compounded in a way that it will give you the most interest back. So this is the best formula for you. Okay, so if, you always want something to be compounded continuously if you're getting interest on it. Okay, so there's no more n anymore. We're not compounding quarterly or anything like that. So let's look at an example. Now let's suppose we've deposited $200, right? So we want to see how much is left after a certain amount of time into an account that's compounded continuously, so times e, with a rate still of 0.02. Remember, the rate doesn't change. And we're going to multiply that times the number of years, which is 10. Let's see how much was earned this time. Okay, so we're back to our calculator here. We get 200 times e. Notice the e is over here next to the ln button. It's a yellow button, so again we have to do second e. It already puts a parentheses for you. We're going to put 0.02 times 10 and close the parentheses. And it gives us $244.28. $244.28. So a little bit more, not much more. So what is it, 12 cents more? Right? And but this is just with $200, right? You can imagine that with more money and with more time and with a higher interest rate, right, the compounding something continuously will get even better. So the point is that it's better than compounding it in some other way. So you try this example. How much was originally deposited in an account that reached $1,000 after being compounded continuously for 5 years? So how much did you originally put in there? So now okay, I'll give you a second to think about that. Okay, so now you know that you ended up with $1,000. You don't know what the original amount was, but you know you compounded continuously, so times e. You know the rate was 5%, so 0.05 for 5 years, so times 5. How do we solve for that? There's lots of ways we can solve for that. We're going to use the calculator to do it graphically. So we're going to say instead 1,000 is equal to x, since we don't have a p variable in our calculator, e to the 0.05 times 5. Okay. Okay, and actually what we're going to do is one more step. To solve for x here, notice we're almost done solving for x, or p, whatever you want to call it. We just need to divide both sides by e to the 0.05 times 5. Divide by e to the 0.05 times 5. Because then it would cancel on the right side, and we would be left with x. And on the left side, we would be left with 1,000 over e 0.05 times 5. And that's what we're trying to find, x. So we need just that number. So let's look at the calculator. Okay, so we're back, and we're just going to type that in directly. 1,000 divided by, I'm going to put all of that stuff in the bottom in parentheses. Divided by, open parentheses, second e 0.0505 times 5 close parentheses, close parentheses. Looks like we needed to start off with about $778.80. So X is approximately $778.80. After 5 years, you would be left with $1,000. Okay, now you're ready to start homework 5.2.